Hello friends, welcome back to Secret of Electronics. In this tutorial, we will explore how a op-amp based non-inverting voltage comparator works and understand its operation in step-by-step in simple and easy understand way. A non-inverting voltage comparator is an op-amp circuit used to compare two voltages. In this configuration, the input voltage Vin is applied to the non-inverting terminal, while a reference voltage Vreference is applied to the inverting terminal. The op-amp continuously compares these two voltages. If Vin becomes greater than Vreference, the output quickly switches to the positive saturation level, which means the output goes close to the positive supply voltage of the op-amp. Similarly, if Bin is lower than Vreference, the output switches to the negative saturation level, meaning the output goes close to the negative supply voltage or ground. In simple terms, the comparator output can only switch between two extreme voltage levels, high or low, making it very useful for threshold detection and signal level comparison. This circuit shows a non-inverting voltage comparator using an LM741 operational amplifier. In this configuration, the input voltage Vin is applied to the non-inverting terminal of the op-amp, while a reference voltage Vreference is applied to the inverting terminal. The reference voltage is generated using a voltage divider network formed by two equal resistors R1 and R2, 10 kilo ohm each, connected between plus 12 volt and ground, producing a reference voltage of 6 volt at the midpoint. The LM741 op-amp is powered by a dual supply of plus 12 volt and minus 12 volt, which allows the output to swing toward the positive or negative supply levels. The comparator compares the input voltage with the reference voltage and provides the result at the output terminal Vout. Now on the screen, you can see that I have created the same non-inverting voltage comparator circuit in simulation software. On the left side, you can see the circuit, and on the right side, you can see the voltage waveforms. In these waveforms, the light blue line represents the 6 volt reference voltage at the inverting terminal of the op-amp, which is generated using a voltage divider. The orange line represents the input voltage at the non-inverting terminal, which is currently 5 volt. The red line shows the output voltage of the op-amp. At this moment, the input voltage is 5 volt, which is lower than the 6 volt reference voltage, so the op-amp produced negative 12 volt at the output, which is the negative saturation voltage. Now as I increase the input voltage, you can see that when the input voltage rises above 6 volt, the op-amp output switches to positive 12 volt. This happens because the input voltage becomes greater than the 6 volt reference voltage. If I reduce the input voltage again below 6 volt, the output of the op-amp switches back to negative 12 volt. We can convert a sine wave signal into a square wave using a non-inverting voltage comparator. On the screen, you can see a waveform graph. In this graph, when the sine wave voltage rises above 6 volt, the op-amp output switches to the positive saturation level and remains at that level until the sine wave voltage drops below 6 volt. When the sine wave voltage falls below 6 volt, the op-amp output changes to the negative saturation level and stays there until the sine wave voltage rises above 6 volt again. Each time the sine wave crosses the 6 volt reference level, the output of the op-amp switches between positive and negative saturation levels. Because of this continuous switching, the sinusoidal input signal is converted into a square wave signal at the output. In this simulation, on the right side of the screen, you can see the waveforms. Here you can observe that our input sine wave signal has been converted into a square wave at the output. If you liked this tutorial, then do not forget to like, share and subscribe. If you want more tutorials, like this tutorial, let me know in the comment section and I will try to create more tutorials like this tutorial in future.